guys, welcome back to the Tech Check for Season 2, Episode 17. Before we begin, here's a word from our sponsor.
Today's sponsor is Anchor. If you haven't heard about Anchor, it's the easiest way to make a podcast. Let me explain. It's free. It has creation tools that allows you to create and edit podcasts right from your phone or computer. Anchor also distributes your podcast for you on multiple platforms such as Spotify and Apple Podcasts. You can make money with no minimum listenership, and everything is in one place to create a podcast. Download Anchor on the App Store or Play Store, or you can go to anchor.fm to create your podcast today.
All right, guys, welcome back to the Tech Check. Today we have Carl. So, Carl, can you tell us a little bit about Muse and what you guys do?
Yes, my name is Carl Copeland. I'm the founder and CEO of Mµz Motion, and we have developed the next generation of high performance motor systems. Most people don't really see how much they interact on a daily basis with electric motors, but to give you an idea, closer to 65% of all of the electricity generated or produced in the U.S. is consumed by an electric motor. So your smartphones have electric motors for the vibration mode. Every single appliance in your house has some form of a motor. Even things you might not think about as being motorized, like computers and other electronics, have cooling motors and sensors and gyros which run on motors. So motors are pervasive throughout through our technology, our modern technology. And so we've developed a new type of magnetic system that produces a next generation motor. Um, and that motor that we're producing, what we've basically done is eliminate 85% of the steel in that motor. So that means that we can we got rid of the steel and we can now replace that steel for structural strength with any other material suitable for the job. And that results in a motor that can be less than 10% the size and weight of a normal motor for the same job.
Yeah, thank you about for all of that. Could you also go into how this would intertwine with your racing team? Give a description for our listeners about your racing team.
Yeah, sure. So a couple of years ago, I was a part of a startup accelerator out of Austin, Texas, and called Mass Challenge. I was one of the top finalists in 2019 there. And while a part of that cohort, I was introduced to this new startup league called Air Race E. And there was a traditional league called Air Race One. And the CEO of that league became convinced that it was time for him to focus on the future of electric aviation as part of this race team. And what most people don't realize is that Formula One racing has really driven all of the technology that we take for granted in our modern vehicles. So F1 racing really defined our current state of automotive technology. And so he wanted to do the same thing for electric aviation. So he created this new Formula Electric air racing class. And I had the privilege of being introduced to them very early on and when I was looking at when I first was introduced to this league, I was like, man, you guys have no idea what you're doing. Like, I mean, there's a reason why we don't have electric planes flying right now. The technology just is not there. Electric motors are very strong and very good at what they do, but they're really, really heavy. I mean, like what's considered a very, very good torque density for an electric motor is 1.4 pounds per 1.4 kilograms per kilowatt. And actually that's considered a very high efficient motor. Most of them are closer to 2 kilograms per kilowatt. And so when you think about trying to put that on an airplane, you're flying a giant steel boat anchor, right? And then you put the batteries on top of that. So I was first looking at that, and of course, being aware of my technology, understanding motors and motor systems and power and controls, I was looking like, man, you guys really, you have no idea how near impossible the challenge you're setting for yourself and the time frame you're setting it in really is. And then but in the back of my mind, I was like, man, how I would love to do something this cool and take my technology into it. And a few days after thinking about it, it went from being the dumbest idea I ever had to being one of the best ideas I ever had. And I realized I had the most extreme motorsport, most extreme spectator motorsport on the planet where I could demo my technology. I mean, air racing below 10 meters, 250 miles an hour, 8 planes at a time, wingtip to wingtip. You're not going to get a more extreme spectator motorsport. So I threw my hat in. I became one of the founding teams. So I'm actually I'm the only official team in all of the Americas. That's North, Central, and South America. All of the other official teams are in Europe. I think we actually just signed one recently from Malaysia, but other than Europe and Asia, I'm the only one in all of the Americas. Yeah. Um, so um, I I threw my hat in the ring on that, and knowing what my technology was and what the technology could do, I realized it was the perfect opportunity to demonstrate that.
All right, cool. So I guess I'll just ask my follow-up question here to what you said. So I know you mentioned like electric planes. So do you actually think that electric planes could actually like happen in the future, like commercially? Or do you think the technology just kind of won't really ever get to that point where electric planes will be used that often?
That's a great question. So the number one problem with electric planes is the ability to carry enough energy with you to make it a viable trip and to be able to refresh that energy quickly enough to make the trip back, right? So if you think about a traditional plane, it flies somewhere, it's burning up fuel as it goes. Actually, as it's burning up that fuel, it's getting lighter, so it's getting more fuel efficient as it continues to fly. It lands, and within a few minutes, it can be refueled and sent back up in the air. It may be half an hour, but still, it's not a 8 to 12 hour charge, right? Like you would think of with a Tesla car or something like that. And so that's the real conundrum: is when you're flying with batteries, that weight is the matrix to hold electrons. And so again, you have what's called a power density issue, where you may have like 400 kilograms. Uh, I'm sorry, like one of the holy grails that Tesla kind of put out there, I think is Elon actually tweeted it. He said that electric aviation would be viable if they could get 400 watts out of a kilogram of battery. So that's a very high, it's a very high weight for a small amount of power. And so that's the real challenge: is how do you carry the energy, and how quickly can you, like, even if you can fly 400, you can use 400 watts per kilogram to get somewhere. How long before you recharge that system? My personal feelings are that everyone has this all or nothing mentality, right? It's like it's either got to be gas or it's got to be an all battery electric plane, and that's really quite foolish. And I say that because you think about, let's take, for example, to me, one of the great examples of a hybrid. It's been a hybrid vehicle since the 40s, and that is called a locomotive. So in 1938, 1939, GE revealed their new diesel electric hybrid locomotives, and that's still to this day what we use. They've constantly upgrading the motors and the generators and all that, but it is a diesel motor that powers a generator. That generator powers what's called a traction motor. That's the really high power, high density motor. You can think of the motor kingdom as an animal kingdom. So on one side, you have what are called high performance motors, like a servo motor you'd use in a robotic application. That's a Hummingbird. Massive precision and performance. I mean, you can't beat the performance of a Hummingbird in its wing, but it has no lift capacity. You can't ride one, right? On the other end, you have a bull elephant. That sucker's lots of power, but not a whole lot of finesse and accuracy. I mean, it's a big, brutish animal. And then you have kind of motors in between: plow horses and greyhounds, and cheetahs and lions. You have all those different strength and performance, but you're always trading the highest in performance for low load capacity, or the highest load capacity for the lowest performance. You're always trading those. And so what the locomotive does beautifully is it takes what is best about fuel: diesel, high energy density, almost 100% energy in that fuel, right? And then it uses that, and it uses a high torque, low RPM. It's a combustion engine that relatively low RPM, high torque. a diesel engine, and that's what an electric motor is really ideal at. The difference between a combustion engine and electric motor is that a combustion engine, it has to get to an optimal or peak RPM to get maximum power. So you think about high performance sports car. Well, that sports car guy has to get to 3,000, 4,000 RPM. Funny cars like 10,000 RPM, right? In order to get their maximum torque and power. So they're really very weak on torque, and they're using speed to make up for it. A diesel engine is a little bit stronger on the lower RPM, higher torque spectrum. So you use something like that to create the mechanical power that you put into a generator. That generator will give you a very high efficiency of a conversion. And then it can send that power to these very high torque, low RPM motors on the axle of the locomotive. And because they're so high torque and they don't need to have high RPMs, you can get rid of any kind of gearbox or transmission called a drive. And therefore it can direct drive the axles of the train. So you can design the motor for its optimal load characteristics, and you can design the motor to drive the generator at those optimal power supply. So what you wind up with is, in the 90s, I used to see billboards out in the West Texas, in the farming areas where I had lived in my teen years. I used to see billboards when I go back there that that said that were showcasing a GE locomotive, and it said, this locomotive can pull 100,000 tons of cargo 10 miles on less than a penny. That gives you an idea of how energy efficient these hybrid systems are. So for me, the future of electric aviation starts with a hybrid system. I mean, until we develop cold fusion, then the best energy density you're going to get is out of a liquid fuel. And so if you do a hybrid system where you have a fuel-based system that is much more it's almost all pure energy per kilogram, right? And then you have that fuel in the system, run it through a very efficient generator set, and then you power electric motors, which are very efficient at applying that force to motion. That's what I think electric airplanes need to be. There's of course a mad race for developing other types of electric energy storage, batteries and supercapacitors and things like that. But to me, for electric aviation to truly be viable, what makes the most sense to me is to produce a clean burning fuel and to produce this fuel electric hybrid system. I actually have a friend and colleague that they formed a new energy company where they can take natural gas and they can convert it into liquid fuels. They can convert it into a pure diesel or a pure kerosene, which is really what aviation fuel is. Aviation fuel is a highly refined kerosene. But the thing is, because they made it out of natural gas, the only emissions is water vapor and CO2. It's a very natural, very clean fuel. So you take a fuel like that, match it with a motor designed to burn that fuel at a high efficiency rate, create a hybrid system, and let all your drive motors, I've already got a design for an all electric multi-stage turbine. So stuff like that is to me the future of aviation in the short to mid range.
That was a lot of good information right there. So what I basically got from that pertaining to our next question, at least, you talked about how one of the main problems between the balance of motors is balancing fuel and electric and the pros and cons of both, correct?
Yes.
So diving back into your motor company, Mµz Motion, how does the motors you develop in Mµz Motion approach this issue?
So the first thing that really the primary benefit of the motors that we're producing is the fact that we have significantly reduced the size and weight of the motors. So where a great example of that would be, take a robotics application, for example. If you have the Atlas robot, are you guys familiar with the Atlas robot that Boston Dynamics is always showcasing? Does the backflips and the parkour and all that.
Yeah. The big guy with the metal frame and everything. Yeah.
Yeah. So that robot is hydraulic. And that's what most people don't know, is that the motors and the joints are hydraulic motors, and they are powered by a battery pack that runs an electric motor that drives a hydraulic pump. And then all these valves have little electric actuators that turn the flow of the hydraulic fluid on and off in reverse direction. And because electric motors are not strong enough to power that robot. they have to use, and even those hydraulic motors are at the end torque capability, right? And so they're kind of doing a hydraulic electric hybrid there, where but part of it is because why the electric motors aren't strong enough is they're so heavy that if you were to put motors in the wrist of the arm of a robot, the motor in the shoulder has to carry its weight, the weight of the motors in the elbow, and the weight of the motors in the wrist at a cantilever of however long that arm is. And so, and as you know, your torque goes up to the square of the increase in distance, right? So the longer the arm stretches out, the torque required to support it, it goes up with the square of that increase. And so that means that the motors in the wrist are so heavy that the robot can't lift its own motors, let alone a payload. And so that's the real issue, is the weight of the motors compared. That's again back to torque density, which I mentioned earlier. The thing that we have is our motor, because we've eliminated 85% of the steel, we're able to replace that steel with ultra lightweight composites and metamaterials. To give you an example, I have sitting on my bench the world's first and only paper motor. I also have the world's first and only 3D printed motor. And in fact, the race plane for our race team, Mobius Aero. So the team I founded that I mentioned before is Mobius Aero. And you can find out more about us and the league at our website, mobiusair.com. But that plane, when we're done, will actually be the world's first and only production 3D printed motor that will be powering that plane. And so we will literally print the motor, the majority of the motor, and have a production motor that's completely 3D printed.
Oh wow.
Yeah.
Just diving on the 3D printed portion of that, what material is used? Do we use resin or PLA or something other than that altogether? Because there's probably got to be a lot of moving parts there. Got to be pretty resistant to outside forces, that sort of stuff. So I was just wondering what material you use for that.
So we have a partner on the race team that is a large 3D printing company, and we're about to do a big kind of announcement on that. So I'm going to hold back on identifying them, but they are doing the 3D printing for us, and they have a multitude of materials that are commonly available to everyone now, actually. But so we have some very high strength, high temperature resistant polymers. And so that's what, anything that's close to a coil or a magnet, we're pretty much going to make out of that material, because it doesn't have any properties that will interact. You have something when a magnet's field is changing near a piece of steel, you have something, or a wire, you have inductance, right? Induction. So it's going to create a field that kind of keeps that magnet from wanting to move. It's force and counterforce, Lenz's law. So we're making we're making some parts of the motor out of these high temperature filament. And then other ones like this part right here, I know that we're a podcast, so that your listeners can't see this, but this is one of the things we're using is a carbon fiber infused 3D printed material that gives us carbon fiber strength in a monofilament. And so we're using those kinds of materials to 3D print the motor. And so basically the fixtures that hold the magnetics are still going to be the same as any other motor as far as the material. Copper wire, something called electrical steel or grain-oriented silicon steel. It's just steel that's been optimized to transmit magnetic fields. And so you have steel, copper, and then ceramic magnets. So those things are there, but we've eliminated 85% of the steel and even reduced the magnets and the windings to optimize those. And the rest of the structure is anything that can support the weight. And the way the design is made, we can actually get by with some very frail materials. For instance, I mentioned before that I have a motor made out of MDF or paper, which MDF, so it's medium density cellulose fiber. It's a type of material you would make really cheap cap, right? MDF. It's glorified paper. We machine the motor out of that. But there's other even more exotic materials. Like, have you ever heard of Aerogel?
So I've heard of it. But
yeah, they call Aerogel solid smoke. It's 99% air. Only 1% of the mass is the material it's made out of. It's a nano foam. And they actually it was developed by DARPA for NASA, and it's the highest thermal coefficient of any material we know of, which means it's the highest insulative value. But it also has the highest strength to weight ratio compressively. So if you put a weight on top of it, it can hold over 1,000 times its own weight. But it's brittle because it's made out of silica. But that thing is, but again, it's 99% air. They have another version of it that's made out of a polymer that has the same similar material properties to this MDF I used, and it's 98% air. And so it's still very, very, very light, but very strong and machinable. So imagine small motors out of that. Now, clearly, it wouldn't be strong enough for larger, higher torque motors, but you can make tiny motors out of it all day. So when you think about aerospace applications where it costs you $10,000 a pound to put something into orbit, and we can eliminate 85% of the weight in the motor by changing the material, then that has a huge economic value for space programs and anything that has to move itself. But keep in mind that like when we're producing large scale motors, we'll probably be injection molding most of those. Once you have a product line, you can afford the tooling, you start injection molding the motors. And that means the price will hit the floor. So um, you can use recyclable, environmentally friendly materials that can be gone through a very inexpensive manufacturing process, injection molding, and you can mass produce these motors with reducing the demand on rare metals, iron, copper, neodymium, samarium, cobalt, those things. You can reduce the demand on those materials, get a higher performance out of the material that you're using, and use recyclable, cheap, economical materials for the rest of the motor. And so you get these very strong motors that over time will be able to bring the price way down. And by the way, whether you're generating power or generating motion, they're all called motors. So a generator is basically a motor with something that inputs mechanical force, whether it's a gas turbine or a diesel engine or whatever it is, or a gas engine. That a generator is the combination of the two. A motor is a motor. A motor is a torque converter. It converts mechanical torque to electrical or electrical torque to mechanical. It doesn't care. And so eventually we will have very small, very lightweight motors compared to today's motors for all these jobs. So going back to the robotics thing, now I have a motor that's a fraction of the weight and much, much stronger. To give you an idea, I built this paper motor, and when we tested that paper motor, it had 10 times the torque of a motor of the same size, of the same class, same size, even though it was made, and even though it's mostly hollow, made mostly out of paper, because some of the unique geometry and configuration of this motor allows us to have a motor that's more active, and the rotor is lighter and closer to the edge of the motor, closer to the radial edge of the motor. And again, that takes us back to the square law, right? Or the inverse square law, which says the further away from a leverage point you go, your torque goes up to the square. So if I have a 1 foot crowbar and I put 1 pound of force on it, then I get, X torque, right? I get 1 foot pound, 1 pound at 1 foot, 1 foot pound of torque. If I make that a 3 foot crowbar, I don't have 3 foot pounds of torque. I have 9 foot pounds of torque. So, because I get to go up with that, I have an increase of 3, so I get 3 squared in the torque. And so that, because of increasing where the rotor meets the stator, increasing the radial distance on the rotor to stator relationship, and get rid of most of the weight, and having most of the motor active, we have a much higher torque density for a much lighter motor. And so whether it's an airplane or a robot or a spacecraft, there's huge weight advantages. All of that goes into making the whole system more energy efficient. A good example of that are quadcopters and racing drones. So most people don't know that they engineer those motors to be about 65 to 70% efficient. The reason why they do that, and again, now let's go back and talk about what really is energy efficiency in a motor. It's really heat loss. How much heat are you willing to throw away? How much energy can you throw away in heat in order to get the torque density in the motor you're looking for, right? So if I had a 99% efficient motor, it's going to be a big chunk of steel. And it takes a lot of battery to lift that big chunk of steel. So even though the motor is 99% efficient, the whole system is very, very inefficient because it's lifting so much weight without any other payload, just from the motors. So you make the motor 60% efficient, 70% efficient. You're throwing away 30% of your energy going into the motor into heat, but you can lift more. And so you actually get better battery life out of a lower efficiency motor because of the weight savings. So what my motor allows us to do is to go into a motor that's over 90% efficient, but we don't have all that weight. We also cut down the weight significantly. So you get a better use of your energy and a longer range because you get a higher payload limit instead of the airframe itself being most of the payload.
So I just had a question about the advantages that I saw on your website of Muse motors, and I saw that you listed that little to no sensors was an additional advantage. I was wondering if you could elaborate on how that's advantageous.
Yeah. So in most high performance, that's really specifically talking about higher performance motors, but not exclusively. So um, uh, one of the primary classes of motors that are out there for robotics and other type applications are called DC brushless motors or brushless DC motors. And so those motors um, really have to have some kind of knowledge of where the rotor is in order to identify itself, right? So I need to know where that rotor is so I know which coil to fire next to make sure that the rotor is doing what I want it to do. And if you don't have position sensing, then you lose track of the rotor and the motor thinks it's working but nothing's happening because the timing is all off. And so all of these motors have to have some kind of a sensor. And clearly, the higher performance the motor, the more you're going to rely on sensors to know exactly where that motor is and what it's doing and adjust the controls to accommodate that. The thing with my motor is that we can use the coils themselves as sensors. So we can kind of do a firing sequence around the motor, locate based on the results of that firing sequence, locate where the rotor is, and then adjust our timing on firing the coils at full power to get back on track and find out where the whole system's operating. A lot of these motors, these brushless motors, use very expensive sensors called Hall effect sensors, which they're very accurate, but they're really expensive, and they'll have multiple of these. Especially on like a high-end servo or something, they'll have multiple of these sensors in there, and that's most of the cost of some of these motors is the sensors and the electronics to use those sensors. And so one of the benefits is, again, based on what the motor is being designed to do, we can greatly reduce the use of those sensors, or in some cases, possibly eliminate them by using the rotor itself. And so probably for context to this, I should probably tell you a little bit more about the motor's configuration. What I've done with the motor is I've actually fragmented the magnetics in the motor, meaning I've taken what's normally a couple, several large windings or a couple of large windings, and I've broken them up into a bunch of small windings. So, for instance, the motors I've been talking about that we've already been running, those are 36 phase motors. We have 36 isolated magnetic circuits, and because of that, we can get an idea of the rotor position by pinging all 36 of those coils, and that'll tell us based on the electrical signal we get back where the rotor is, and we can use that for a sensor. In applications where that's not really viable or we need better performance than to wait for those pings to come back off the coils, we can put much lower cost sensors as well called encoders. You guys might be familiar with encoders. So we can put an encoder on each end of the motor and compare those encoders and always know where the rotor is with a high level of precision without having to buy these really expensive sensors. And so it just basically drops the complexity and the price of the motor compared to same class motors who would be doing the same job.
Nice. That's really cool. So, I guess to like almost close it off, what advice would you give a student that wants to enter motor engineering or aerospace? And is there any specific background that you recommend these students should have?
So first, let me preface everything I'm going to say with this bit of information. I took a very unusual path. I took a very hard, long path. I had a different life than most people have. I was the primary source of income by the age of 12 for my family of six. My brother and I were the pretty much the sole income. I politely asked my parents to leave when I was 19. So I was working full-time jobs while going to school and all that. And I actually had earned some scholarships, but hit a point where I had to decide, do I feed my brothers or do I go to college? And so I moved across the state line my senior year, lost all my scholarships, and I was the first male in my family to graduate high school. My brother, just younger than me, was the first of us to ever go to college. My youngest brother was the only of us to graduate from college. So I took a much longer, harder path. I'm completely self educated. It was not fun. It was not easy. I do not recommend it. Do not get any romantic ideas about what that path was like. But to be just understand, I didn't get here through academia. I got here through perseverance and 20 years longer than it should have taken. So, um, that being said, looking at the horizon and understanding where technology is going, there's two major things that I would say there's three major things that I would encourage you to get as much information as you can get on. Specialize in the mechanics of a motor, understanding the electromechanical physics and properties of motors and transformers. In fact, my motor is actually a transformer, a bunch of transformers that produce a motor. So it's a completely different magnetic system than any other motor you're going to see. We have our unique magnetics fully patented in multiple domains. I have over 30 patents granted. But the thing is that it's a very unique path. So understand everything there is to understand about motors and transformers. You also are going to have a solid understanding of electronic controls, because without modern electronics and without modern electrical controls, these motors aren't viable. My motor wouldn't have worked 15 years ago because the electronics for this motor didn't exist 15 years ago. I invented the system 25 years ago. I've been working on it full time for 10 years, and I would say even 5 years ago, the electronics weren't really viable like they are now for this type of a motor. It's very complex, and so having a solid background in the mechanical side, the electromechanical engineering, also a good understanding. You're going to work with experts who are focused and specialized in the field, but you as the motor person need to also understand how these motors are being driven or can be driven. So you're going to want a strong electronics with some software, like some C plus level, compile language level software knowledge. You don't have to be the expert. You just need to be knowledgeable. And then I would also um, put some time into material sciences, because that's the one thing that we've really not even touched on our motor system. I've been working on this for a long time, and I've only just picked a couple of materials that either, like the paper motor. No, nobody wants a paper motor. Trust me. I mean, it's not a viable material for a production motor. It was a publicity stunt, right? I wanted to show, I probably would have been better off making the thing out of mud, actually. I wanted to show if I could make it out of paper, I could make it out of anything. I mean, this MDF motor, every time I change rooms, I have to retweak it to get it to run because the paper moves so much with humidity and temperature. And so, but again, I was demonstrating the material diversity of this new platform. But there's miles to go, just specing the right material for the right job, developing new materials for new properties. So to me, again, understand the electrical mechanics, understand the electronics that'll have to control it, and spend some time getting really familiar with materials and material sciences. Those would be my recommendations. I would
Thank you.
also like to back that up with, do not let academia put your thought process in a box. They want to hammer into you their methods and formulas for doing it. And they all scream that if you don't do it this way, it's impossible or it's wrong. Everything I did in developing this motor called wrong. And I proved dozens of so-called experts wrong the first time I drove this motor with controls. They said it couldn't be done, and I did it. So obviously you want to have qualified your ideas, and you want to know that there's you want to have figured out it can work, but don't let narrow-mindedness push you into a box. I used woodworking techniques and metalworking techniques and all kinds of trades I learned growing up. I use that in developing this motor, and so you want a diverse knowledge base as well.
Thank you. We really appreciate that. I'm just gonna close off by saying we'll put all of the information for to reach Mobius Air and Mµz Motion in our description on social media, wherever it may be. So definitely, I would recommend to check them out. Mr. Copeland, I'm pretty sure if they want to contact you, they can, right?
Absolutely. Yeah, absolutely. Don't hesitate.
All right. So again, thank you guys all for listening. Thank you, Mr. Copeland, for joining us on the Tech Check. We really appreciate it. And
My pleasure.
stay safe and stay tuned for the next one. Thank you guys.
Same. Thank you guys.